We spend so much time learning how to normalize databases, remove redundancies, and split table apart so that we can avoid anomalies. But here's the twist. Sometimes we put redundancies back on purpose. Sounds backward, right? Why would we undo what we just worked so hard to achieve? Think of a normalized database like a clean modular circuit. Every component has one job, but sometimes performance demands a shortcut while connecting distant parts directly. That shortcut saves time, but makes the system more fragile. Denormalization is that shortcut in database design. Imagine a dashboard that joins 5 tables to display a report. It's perfectly normalized, but every query takes seconds. Your users don't care about perfect design. They care about speed. Denormalization is one of the ways that we trade a little data purity for performance. In this video, we'll see what denormalization really means, why it's sometimes necessary, and how to do it responsibly. Let's start by properly defining denormalization first. Denormalization is a last-ditch database optimization technique that intentionally introduces some redundancy to a database to improve query performance. It typically involves 2 steps. The first step is to identify queries that are used frequently and require joining more than 2 tables. The identification process requires you to observe how users use your database and gain empirical data first. The second step is to decide whether and how to duplicate some columns in the identified tables so that it can reduce the number of tables that are required to achieve the same result. Let's illustrate this with some examples. Think about a music app like Spotify. You design its database, and you are responsible for optimizing it now. One thing that you noticed is that the query that retrieves top songs of famous artists are executed frequently. Yet, famous artists have typically issued many different albums, and songs are associated with album table instead of artist table in the database. That said, this query always needs to join 3 tables together in order to retrieve top songs from famous artists. Like what you have seen here on the screen, 2 one-to-many relationships, and a cumbersome SQL query that joins all the 3 tables you saw. Now you have completed the first step in denormalization. You have identified the query that is frequently used and requires joining more than 2 tables, and you have found solid evidence that this query takes a bit longer than what users expect for a very basic task. After trying all different optimization techniques, you realize that none of them works very well, so you decided to apply denormalization to address this issue. We already know that the only way to associate an artist to a song is via the album table. To reduce this middleman table, you can build a relationship between artist table and song table directly. The link between the 2 tables allows you to bypass the album table whenever you need to find the top songs from a famous artist, which will simplify the SQL query. Of course, the old query on the left side needs to join 3 tables, but now you just can join 2 tables to achieve the same result at a faster speed. Sounds awesome, right? Such a change doesn't come without a cost. If you focus your attention on the album table, you can tell that it's in a classical one-to-many relationship with artist table. And the foreign key, artist ID, is in the album table. Since the primary key in a table functionally determines all other attributes, we have this functional dependency. From album ID to artist ID, or say album ID functionally determines artist ID, because album ID is the primary key in the album table, and artist ID is not a primary key. As a foreign key, it's functionally determined by the primary key. Similarly, If you focus your attention on the Sun table now, it's in two one-to-many relationships with both the artist table and the album table. And both the foreign keys are placed in the Sun table, including album ID and artist ID. Since the primary key in a table functionally determines all other attributes, we have this functional dependency that goes from Sun ID to album ID, or say the Sun ID functionally determines album ID. If you put the two identified functional dependencies side by side, you can clearly see that they would form a transitive dependency like this, which violates the third normal form. Now, you have completed the second step in denormalization, and perhaps have a better understanding of why it's named denormalization, because this change will lead to a violation of normal forms. That's the cost of increased speed and simplified SQL query. To make sure that we are on the same page, let's look at another example. Think about a database that supports an online shopping store that you design and manage. After a few months of operation, you noticed that this query that joins three tables together is performed frequently. The three tables include user, payment methods, and purchases. As users view their order history, they will keep triggering the query that joins users and purchase table. Yet the two tables are not directly related to each other. To join the two tables, you have to go through a middleman, which is the payment method table. As time goes, you realize that this query is triggered so frequently that it warrants some optimization. That said, you have completed the first step in denormalization. You have identified the query that is frequently used and require joining more than two tables. And you have found evidence that this query takes longer than what users normally expect for a basic task. After trying all different optimization techniques, you realize that none of them works very well, so you decided to apply denormalization to address this issue. To reduce the number of tables that need to be joined, you can add a direct relationship between user and purchase tables. By doing so, you can bypass the payment method table to complete the same task. As you can see, this change will lead you to join two tables instead of three tables to achieve the same result. The updated SQL query is much more simplified in comparison. Of course, the newly gained efficiency and simplicity has some cost. If you focus your attention on the payment method table, it's in a classical one-to-many relationship with user table, and the foreign key is placed in the payment method table. We know that the primary key functionally determines all other attributes, including the foreign key. So from payment method table, we can deduce this functional dependency that goes from payment ID to email, or say payment ID functionally determines email. Now, if you focus your attention on the purchase table, you can see that it's in two one-to-many relationships with both payment method and user tables. And it contains two foreign keys, including payment ID and email. Since the primary key determines all other attributes in a table, we would have this functional dependency that goes from purchase ID to payment ID. If you put these two functional dependencies side by side, you can tell that they can clearly be chained up to form a transitive dependency, like this, which is in violation of the third normal form. Now, you have completed the second step in denormalization and gone through two examples. It's time for us to discuss the best practice on denormalization. Denormalization may sound tempting, but you want to be careful and never misuse it. For example, you don't want to denormalize unless you have measured a real performance problem and tried other approaches first. For another example, if your tables are updated often, like inventory, balances, or user profiles, redundant fields will quickly fall out of sync. In such cases, denormalization can lead to disastrous results. Think about when you need to duplicate a customer's address in multiple tables. As addresses are updated, when your customers move, their data will become a nightmare. Or when your database has a relatively small size, drawing on small or indexed tables are usually very fast, even if multiple tables are involved. In such a case, denormalization gives no measurable benefits. Or if you work in a corporate environment in which multiple teams or systems write to the same tables, denormalization would complicate coordination and increase the risk of inconsistency. Now, you may think that I have cautioned you against denormalization and wonder what other techniques you should try first. Let's talk about them. First, you certainly want to start with indexing the columns that are frequently used for sorting, ordering, and filtering. Next, based on indexing, you want to rewrite your queries to use better drawing order, window functions, or aggregations. This often brings huge gain without schema change. Beyond indexing and query optimization, you also want to try caching. Application-level cache, like Redis or Memcached, can help reduce repeated read load. Or even better, you can keep your database design normalized and only denormalize it in cache. If all these techniques fail and you still urgently need more efficiency, then you move to denormalization. If you have to denormalize, you want to document redundancies explicitly in your README file, and work with your backend developers to use triggers to propagate changes automatically when the source data changes. You also want to run consistency checks to detect divergence between redundant copies and verify that performance improvement would justify the added maintenance complexity. In this video, we covered what denormalization is, used two examples to explain its consequences and trade-offs, and discussed the best practice on denormalization. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment.